Okay, good evening, everybody. Let's start today's discussion on the stereochemistry assignment 8. Let's start. Can you see my screen?
Yes, sir.
Okay, so let's start with the first question. So here it is saying that predict the measured stereoisomer formed in the following reaction. So before starting with this question, let us talk about some rule. Let's first start with our discussion with the Cram's rule. Okay. Okay, so Cramp's rule accounts for the preferential formation of one diastereomer in terms of the steric interaction. Okay, so let's assume an example that there is some stereo center, there is some carbonyl group is there, and in adjacent to carbonyl group, there is some stereogenic center is there where the three groups are present, where. Can you see my screen?
Yes, sir, we do see.
Okay. So let's start with this example that a carbonyl group is there and adjacent to carbonyl stereo center is there. So the Cramp's rule say that the attack of the nucleophile to the carbonyl carbon will occur from the less hindered side, and the carbonyl group is flanked with the two medium and small group is there. So let us illustrate with this example. We will draw the Newman projection of this molecule. Newman and the backside carbon, there are medium group and smaller group, and here the large group is there. Okay, so let us start. There is some, this is the nucleophile chelated with the metal like various reducing agent or various Grignard type reagent you may have. This M is metal. Okay. Okay, so there is two possibilities of attack in this molecule. This M is metal, okay, and this is the medium group which is on the carbon. This is group, and this M is metal. So it is chelating. This metal is chelating with the carbonyl carbon, and this R dash. This is the nucleophile. This may attack in this direction. So our product is. Can you please mute yourself? So this is one possibility, and another possibility comes here. So the R dashed may also may attack from the this direction, from the side of the medium group, and the product will be. So tell me which one is the major product. This side, the R dash is attacking from the side of the smaller group, and here R dash, that is nucleophile, is attacking from the side of the medium group. So can you tell me which will be the major product depending upon the uh, steric interaction? Anybody? This one or this one?
Nucleophile prefers smaller group, I guess so.
Yes, exactly. So when the nucleophile is approaching from the side of the smaller group, this attack is definitely favored from the steric interaction point, and this is the major product, and this is going to be the minor product. Okay, any doubt? Anybody? So let's concentrate on today's our problem. So the model I discussed in the general part. So this model is called the open chain model. Okay, which model I have discussed here. This model is known as the open chain model. Okay, so now let's focus on the problem given to our question. Let's discuss. So now in this part, we will know that if one of the substituent on the stereo center, which I have designated in the previous problem as the small, medium, and large, if one of the chelating groups, okay, if one of the chelating groups like OH or NH2 or OR is present on the stereo center of the carbon, then some different model we will go through, and let's discuss on that. So the stereochemistry of the product then not will be guided by that open chain model, and then will be guided by the this metallic chelate will be formed. Okay, so let's focus on our this question. In our question, there is stereochemistry of the stereo center is already defined. There is OH and there is ET, and here carbonyl carbon is there, and Me. So can you tell me along among these three groups, hydroxyl, phenyl, and the ethyl, which one is the largest one? Large group?
Phenyl,
Exactly, phenyl. Then medium group,
ethyl.
ethyl, and the OH will be the smaller group, right? So we will see how that five-member chelate ring is formed in presence of, as there is some in stereo center, there is some hydroxyl group. So hydroxyl group can form chelate complex with the metal. So this situation will somehow different from the open chain model. So let's see. So with the OH group, the chelating group will orient itself like a way that it may form chelate complex with the both the carbo. It will orient itself in such a way that it can form chelate with the both hydroxyl oxygen and the carbonyl oxygen. Okay, and here phenyl will be there. So phenyl will attack from the side of the, this is the large group L group and this is the medium group. So definitely it will attack from the side of the medium group to the carbonyl, and our product will be, okay. So this will be our final product. So can you differentiate between two? This was the open chain model. There was no some chelating group on the stereo center. So this is the nucleophile will attack normally from the smaller group to predict the major product. But here, as that OH group is there on the stereo center, so this will form a 5-member chelate 1, 2, 3, 4, 5, and the nucleophile will attack from this side. So if we rearrange this, so if we match with the given option in our question, so it matches with our option D. Okay, so there we get the Newman projection. So if we rearrange according to the flying wedge, so this is our major product. Okay, any doubt? Anybody? Hello? Hello? Anybody?
No, it's okay,
No,
sir.
no,
Clear. Go for the next problem, sir.
clear, clear.
Okay, okay, okay. Okay, so here uh, two adamantane derivative is given and we have to answer this, that which one is the major product in this case. Okay. So this will we will solve according to the C-plug effect. Okay, you know the C-plug effect, what C-plug effect is. So here what happens, the electron density of the existing group donate to form the carbon nucleophile bond. Okay, so here definitely you can get that hydride will attack here and the reduction will take place at the carbonyl carbon. So here at X is two variant is there, that for in first case X is NO2 and in second case X is NH2. So we will consider on only this part of cyclohexane for our solving the question. Okay, so here carbonyl group is there and here is X substituent is there. So what is saying that the electron density of this bond will donate to the forming bond of the carbon nucleophile bond, that the which will new bond will be formed, that will donate to the stabilizing the sigma star orbital of the carbon nucleophile. So, so it will donate to the anti-periplanar bond of the newly formed bond. Okay, so here as we can see that X is equatorial position. So definitely the equatorial bond form will be stabilized anti-periplanar with respect to X, and the more electron donating X is, this equatorial bond formation of the carbon nucleophile will be more favorable. Okay, and this is explained on the basis of the hyperconjugative effect, that more electron rich the CX bond is, so it will donate better in stabilizing the sigma star orbital of the carbon nucleophile at the equatorial position, and the bond will be more stabilized. So from among nitro and the NH2, which will be the better donating capability, which will donate electron better?
So aniline.
Aniline,
NH2.
exactly. Huh.
Yes.
NH2 is the electron donating effect, and the nitro has the electron withdrawing effect, right? So varying electronic property at the 5 position, the NH2 group is better able to donate electron density in forming sigma star CH bond. Here nucleophile is hydride, as we know. So a new carbon hydrogen bond will be formed, and the anti-periplanar attack from that side is favored. Okay, so whenever the this is NH2, this is NH2, means X is NH2, then this equatorial bond formation will be favored. Okay, so our right option is option B. So whenever there is NH2, that the equatorial bond anti-periplanar bond formation will be obviously favored. So let's move to our next question. That is that is same type of the question, that lithium aluminum hydride is attacking at our this substituent, and we have to say which one is going to be the major product. So let's draw the model. So it will form chelate with the lithium aluminum hydride, and the hydride will attack from which side? From the side of hydrogen or from the side of methyl?
From the side of hydrogen.
Side of
From the side of hydrogen, definitely it is smaller group, so it will attack from this side, and our product will be so if we rearrange it to the Fisher projection formula, it will look like and it is matching with the F, given option F, and this is the right option is option B, that F is the major product and it can be rationalized using Felkin and model. Okay, as there is no some chelating group like OH or NH2 present here, so it will be predicted, the product will be predicted according to the open chain model as I discussed first in the today's session. Okay. Okay, the next question is based on the, which name reaction is this? Titanium isopropoxide in presence of minus state, very famous and
Sharpless epoxidation.
exactly sharpless epoxidation is there. Okay, so a specific stereoselective epoxidation takes place, and there is two type of variant, minus state and plus state, right? When minus state we apply, then which stereoisomer will be formed? Above the epoxide will be formed above the plane or below the plane?
Above the plane.
Above the plane. Okay, so which one is the right option here? And this is applicable to the allylic alcohol, right? This allylic, this kind of epoxidation takes place in case of the allylic alcohol when we have. So tell me, which is the right option among the among the given option? Which one is this molecule? This one, A. No, this C. The connectivity is not right here. Here hydrogen and the phenyl are trans to each other, but here hydrogen and phenyl are the cis to each other. Right. So this is also not right. Here also phenyl and the hydrogen cis to each other. So among B and D, which one is the right option?
B.
B, exactly. If we rearrange the structure, if we tilt it to some with some angle, then it will be like epoxide is formed above the plane, right? So B is the right answer. Okay, so what is saying in this question? Um, we have to discuss about the enantiomeric excess and the enantiomeric transition state. So enantiomeric excess means some of the enantiomer has to be in the greater form, more than 50% is there. That is why some enantiomeric excess is there. Let's draw the picture of the enantiomeric transition state, right? Let's suppose it is a transition state A and it is the transition state B. So if we put a mirror uh, between them, so the one transition state will be the perfectly mirror image of the another. So if they are in equal in energy, then both the isomer will be formed in equal form, then there is no enantiomeric excess will not be there, right? And in case of the diastereomeric transition state, if we put a line here, then they are not, they are unequal in energy, right? They are not equal in energy of the transition state. So definitely they are different in the energy. So uh, the probability of forming the product will be different. So a reaction showing diastereomeric excess, where there is one diastereomer is formed in the higher ratio than the another, is greater than zero. That is, there is some more percentage of the one diastereomer as diastereomeric transition state. So option C is the right one. So let's move to the next question. So here we will discuss another model, that is, see here, no some chelating agent is there, right? Like OH, NH2 or any kind of ester is not there. But here some chlorine is there, like chloro is there. So there will be definitely a repulsion. This has a dipole moment. Chlorine is a strong dipole, and carbonyl has also some dipole. So there will be a possibility of the dipole-dipole interaction, right? So to minimize this dipole-dipole interaction, the chlorine atom is favored to keep it is and the anti position with respect to the carbonyl group. So this is called the dipole model. Whenever some strong dipole group is present in the stereo center adjacent to the carbonyl group, then the molecule adjusts or orient itself in such a way that the chloro or the strong dipolar group is anti to the carbonyl group. So let's discuss how does it proceed. So configuration is given R configuration. So this way we can write the R configuration. Okay, so carbonyl is here and the chloro will be anti to the carbonyl group, and remaining will be as it is. Then oxygen will chelate with the metal, and hydride will attack from which side? From side of the phenyl or from the side of the hydrogen? From which side it will attack?
Side of hydrogen.
From side of hydrogen, as this is the smaller one. So hydrogen will attack from this side, and our product is okay. So if we match with the some rotation we give, then it matches with our given option B. So can you got it that when some strong dipole is there, like chloro or other halogen atom bromo is there, then to minimize this interaction, there is some strong dipolar interaction between the oxygen and the chlorine. So to minimize that, chlorine atom is placed anti to the carbonyl group, and the attack will be placed from the side of the smaller group. Okay, any doubt?
No, sir.
Okay, so let's move to the next question. So this is also a very popular model. It is. Can you tell me which model is this? Here a keto group is there and adjacent ester group is there. This is also a very famous model of predicting the product. This is Felkinan model, right? Okay, so let's draw what is given in the question. A configuration is already given there. It is R configuration. Okay, so in this case, that configuration R ketoester is given, so it is treated with the CH3 methyl magnesium iodide. So this is the nucleophile CH3 group. So the methyl group will attack from which side to this carbon? This is the large group, that is C6H11. This is the smaller, as you know, hydrogen is the small group and methyl is the medium. So can you tell me from which side this methyl group will attack at this carbonyl carbon?
From medium group, sir.
No, from the side of the hydrogen, that is from the below plane. Okay. Obviously, the attack will be from the smaller side of the where the steric interaction is the minimum. From this side, methyl will attack at this carbon. And what will be our product? Below the plane, methyl will attack. There will be OH. And it will be as it is. Okay. So methyl, as we know that the methyl will attack from the back side of the carbon. So which phase methyl will attack? The front one is the which phase? This phase from where we are looking at the carbon. This is re phase or the Z phase?
It's rephase.
This is re phase. That is 1, this is 2, and this is 3. Right? So clockwise rotation, it is re phase. So the backside carbon automatically will be backside phase from where the methyl will attack. That will be
Psi phase.
psi phase.
Then it's not reface, so side face.
Psi phase. So which we are looking, this is re phase and the backside definitely will be psi phase. So the methyl will attack from the psi phase, and after hydrolysis, it will give the product that ester will be hydrolyzed, and we will get ultimately so if we rearrange this, we will eventually lead to this product. So the attack of the nucleophile occurs from the Z phase, which we have already seen here, and the product will be after hydrolysis will be this one. Okay. Okay. So let's move to the next question. This is also an example of the that C-plug effect, right? So here the two possibilities of the there. The attack may be done from the axial side, then equatorial alcohol will be formed, and otherwise attack will be may be formed from the equatorial side, then the axial alcohol will be formed. So now we have to check, this is an conformationally biased enantiomeric system. The tertiary butyl group is always in the equatorial position, right? So it cannot flip its position. So we have to see that what is the electron density of these two bonds. Okay, so the more electron dense this bond is, so the more easily it can form the favorable equatorial CH bond. Can you get it? Likewise, I was told earlier in that problem that the due to the hyperconjugation effect, the electron density of the existing group will donate in forming the carbon nucleophile bond, and it stabilize the sigma star orbital of the incoming group. Okay. So here, as we know that the sulfur is has the lone pair of electron. Okay, so it will definitely donate better to this bond. So this bond is very much electron rich, so it will be donate easily in forming the incoming CH bond. So here the CH bond, the incoming CH bond is very highly favored. Okay, so in this way, this order is explained in basis of the C-plug effect, that the more electron rich this bond is, it will easily donate the electron to the incoming carbon nucleophile bond, and this will form the axial alcohol.
Sir, doubt, sir. Hello,
Yes, yes.
sir. In option J, so there is no 1,3 diaxial interaction in option J and option K.
Mm,
So there is a diaxial hydrogens in option L.
mm,
So that's why the incoming nucleophile uh, in the first option J. So that is it can approach the carbonyl carbon more easily in J option. So
mm,
next it approaches the nucleophile in option K. So I think the option is A. I think my opinion, the
mm.
correct answer for eighth is A. J greater than K greater than L, I think. So because L is has 1,3 diaxial hydrogens in L option,
Mm-hmm. Yes.
I think A is the correct answer from my opinion, not D.
Okay.
Because there is no in J and K there is no axial hydrogens, only lone pairs are present on S, sulfur and oxygen.
Mm-hmm.
These two are same group. So
Yes.
oxygen is smaller than sulfur. So that's why attack of the nucleophile in the J option is more favorable than K, and then the list is the L.
Okay.
So check once, sir. I think this
Okay.
is my
Okay. We will discuss. Okay. Yes. We will check it again. That you are saying that due to the absence of the 1,3 diaxial interaction
yes,
between
yes,
K and L, the L will be
list one.
least one,
So
as
the
there is.
hydrate will attack from the so this position, but we will get the equatorial alcohol. So alcohol should be OH group should be in the equatorial position.
Hmm. But here one thing is there, we are considering about the axial alcohol, right? Axial alcohol, and axial alcohol will be formed when the attack will be from the this side, right? From the equatorial side. So we have to consider that direction also, that yes, definitely after forming that there will be some 1,3 diaxial when there it will be from OH, but transition state there is no such steric interaction is there, as it will approach from the equatorial position of the hydride. So from the transition state there will be no some steric interaction. Yes, at the product there will be some steric interaction between this 1,3 diaxial interaction. Okay, we will check it one second. Question. Okay, now tell me what is the correct option for this one? 9. Here it is saying that the second step is the rate determining step. Is this true? Second step, as we know, for being the rate determining step, the delta G has to be maximum, right? So this is not right. We have to choose the right option. So the right option is transition state 2 as the product like transition state, as the transition state is closer to the product. So this is the option A is the right option. Okay, so here the another very interesting problem is there. So this is also we have to explain on the basis of the Felkin and model. Right. So here already product is given. This is the major product and this is the minor product. So if we go with the conformation of this carbon, conformation of this carbon. So among these two, we have to check these two can be the transition state of this starting material. So let's discuss. Let's first start with the A. So here another thing is there that in this model, the nucleophile will attack with the 109-degree angle from the carbonyl group, and this angle is called the Burgi-Dunitz trajectory. They have shown with some calculation that when the nucleophile is attacking with this angle, then the transition state will be more stable. So here electrophile is the methyl group. So if 109 degree, that is from this side, it has to attack, then our product will be so if we this is the transition step we are getting from the one sorry A. Then in case of the B, let's draw this. So tell me which is the transition state. So here, according to this configuration, the C and D are the not right. Means according to this configuration, that A and the B are the possible transition state for the attack. So just follow that when A, we are considering A as the transition state, that is this one, then here we are getting the three syn product or the anti product. We are getting the trio product, right? Like this one. And when we are proceeding with the B, we are getting the minor product. So as major product is the this one, so definitely the reaction has proceeded through the transition state A. Okay. As we proceed with the B, then it is the erythro product. So this is here, as we see, the minor one. So reaction is proceed with the transition state A. So now this is the question. It is saying that this is 1,2-diketone is there, provides you with 100% diaster selectivity and 70% enantiomeric excess. What does it mean? 70% enantiomeric excess favoring the RR configuration. So 70% enantiomeric excess means what is the population of the RR form? That 70% is excess and rest 30% is plus minus racemic mixture. So between this 30%, there is also 15% of RR and 15% of another. So total 85% of the RR. Right? Can you get it? Hello?
Okay, sir. Carry on.
Okay.
Proceed, sir.
Okay. So among this 80% is RR group. So if we try to determine the stereochemistry of these groups, so we will come up that this molecule is the RR, has the RR configuration. Okay. So correct option is D. Okay. So any doubt in Cram's rule? From Cram's rule, any doubt you have?
Sorry, sir. I have another doubt in problem 7. It's my doubt. I'm clear with the answer, but still I wish to need a little bit clarifications.
This one?
Going to the question number 7 that we've been discussing.
Okay. Okay. Yeah. Yeah. This one. Yes.
Question number 7. I think the option D seems to be unclear to me because if it is in the dashed formula, the
Yes. It is
T dash dash
also, yeah. It is three at the in the dashed form, right?
yes,
So the configuration is not clear.
yes.
So anyway, that our desired answer matched with the option B. So we will go with the B. Okay, the psi phase, and if we illustrate, if we draw in the Fisher projection formula, then it completely matches with the option B. So our right option is
If I
this.
Sir,
if I
check
put
once the B option. I think the Fisher projection. I think this is not correct. I think check once, sir. B option.
B option.
So this is wedge dash formula. Convert it wedge formula into Fisher projection,
Yes.
sir. First of all, convert, sir.
Okay, this is the Fisher projection formula of this one.
Sir, from which side you are observing, sir? Two groups, methyl and OH groups are one OH group is on wedge line, CS3 is
We
on
are
dashed line.
giving a 90-degree rotation anti-clockwise so that the OH and the methyl group are on the vertical line, that is below the phenol. We are taking in the vertical line, and if then we are just putting it in the Fisher, normal Fisher form.
okay, sir.
Okay,
Yeah, I'm clear.
thank you.
Sir,
Yes,
sir, can you explain second question again, sir?
second question.
Yes, sir.
This one. Okay, this is we will explain on the basis of the C plug effect. If this effect is saying that when there is some group which is already present in the cyclohexane, so this will donate its electron pair to stabilize the incoming carbon nucleophile bond, and it will donate its electron to the low lying sigma star orbital of the carbon nucleophile bond to stabilize the bond. Okay, so when there is some electron donating group, that is NH2, suppose NH2 is present here as the presence of X means para aniline, para amino benzene, then definitely NH2 group has the better electron donating effect than nitro. Is that clear? NH2 is the better electron donating.
Yes, sir.
Okay, so and you just visualize or forget about the this part. Only see that this cyclohexane part, that this bond is anti-periplanar with the this bond, right?
Yes, sir.
So whenever from this side and the hydride will attack, so CH bond will be formed here. So definitely when there is some electron donating like NH2, or it may vary like NH2, OH, any kind of electron donating group is there, then probability or population of forming this bond will be much higher. So where in this case where X equals to para nitro, so the incoming CH bond, that is carbon nucleophile bond, is favored, as NH2 can donate better electron to stabilize this bond. So this is the case we have ticked that C is the major product from the B, that is from the B NH2, that this side of bond is favored. But here if we suppose in it is nitro, right? So nitro is the electron withdrawing effect nitro has. So it will not stabilize this equatorial CH equatorial bond. So the opposite conformation is formed. That is, hydride will attack from the axial position. This is the fundamental case in this problem. Okay.
Yes, sir. Got
Okay.
it.
Thank you. Okay. Any doubt,
Sir,
anybody?
I have query regarding exam.
Okay.
Sir, is
Mhm.
it on 25th of September or date is shifted?
Uh, Initially it was